So, as we've been looking at applications of the derivative, we have kind of constantly reminded ourselves that derivatives do give a rate of change. Okay? Up to this point, however, our focus has really been on derivative as a rate of change as it relates to motion, typically. Okay? We've really not done much of anything with other rates of change. But the cool thing about this is that it doesn't just apply to motion. It applies to anything where we can write a function for it and there is some kind of a rate involved. Okay? Here are a couple of examples. Let's say the cost, all right? If I were in manufacturing and I were producing a particular item, let's say we're a car manufacturer, okay? If you think about the situation, there are certain costs involved that are fixed. In other words, it costs the same amount to turn on the lights every day, whether you make one car that day or 100 cars that day. You know, you have to pay certain people on salary. You have to pay for insurance. You have to pay for all this stuff. Those costs are fixed. However, there's other costs that vary depending on how many cars you're going to produce, okay? Because the number of cars you produce determines how many hours you have to pay people to work. It determines how many materials you have to buy to make the cars out of, and so on. There's a lot of different things that go into it. So when we're talking about the cost to produce, say, 100 cars in a day, that it might cost a little bit different per car if we make 100 cars than if we made, say, 50 cars in a day. That's what we call the marginal cost. Okay? Sometimes, you know, if you have a little home business or something like that, your marginal cost may not change. You know, you're your only employee, you don't pay yourself by the hour, and you're at your house, so it's not like you're paying extra for facilities or anything. It's just you buy the materials to make it, you make it, and you try to sell it. So the costs are fixed all the time, just based on however many you want to make. There, the marginal cost would be constant. But for any kind of a business that has those fixed expenses, their rate of change in cost is going to be different depending on how many items they produce. And they actually, the idea is you want to find the minimum cost. You might say, well, isn't it just the more we produce, the lower it costs? Not necessarily, because we might reach limits to where, okay, if we produce too much in a day, we're going to have to pay our employees overtime. So now it's not their normal hourly rate, we're paying them 1.5 times their hourly rate. So that actually increases the cost. Or maybe producing a certain number in a day puts too much wear and tear on our machines and we're going to have to repair them more often. So that's going to increase our costs. So every business is trying to kind of work with their cost model to see how can we minimize the costs. Okay? So that's one example. We could talk about things geometrically, like area or volume. Okay? For example, we'll look at one. If we're looking at a triangle where we change the angle, how is the area of the triangle growing as we change just the angle between two sides that we know? Okay? You know, and that can we can look at how fast that area is growing. Okay? Same thing with volume. Now, volume is kind of an interesting one because we could look at things like if we were trying to drain a container that had a liquid in it. We could actually figure out what the change in volume is at a moment by just measuring how much comes out in a second or something like that. However, because of the weight of the liquid, when the thing is full, the water is going to get pushed out faster than when it's only half full. And as it gets close to empty, the water starts to just trickle out. It barely flows out at all because there's not a whole lot of weight pushing it out the hole. Okay? So there you have the change in volume, the flow rate, you could say, is going to decrease as the container gets empty. All right? So you have changes in volume that we can consider using derivatives. A population, all right? If we have a model for our population that we've created by, maybe we did a scatter plot and then we used some kind of a regression model on the calculator to help us develop a model, we could figure out what the growth rate is at any given time. Okay? You know, we're familiar with exponential functions. They might start growing slowly, but then it starts to shoot up. Okay, well, what's the growth rate at a particular moment? Or what if you have something that varies? It's not just an exponential, it's kind of varying. Okay, at one point the growth rate might be a positive, 2%, and then another point it might be a negative 3%. Okay, but using the derivative, we could come up with a function that represented the rate that allowed us to that allows us to calculate it at any moment. Okay, and then if we're doing that, we could then maybe look back, if we're looking back at data historically. Okay, what happened that caused our population to go down there? All right. And we're not necessarily even talking about population of like a city or a country. This might be the population of bacteria in a petri dish, and a researcher's doing the effect of a new medication on some kind of a disease or something. They could look at growth rates. Maybe initially it starts helping, but then it wears off and the bacteria start growing again or something. But we could look at the rates and they can use it however they want there. Okay. So there are a lot of applications that we can use derivatives for. Okay, the key is writing a function to represent them. Okay, that's really the hardest part, is getting that function. All right, so let's look at some examples. Here we have the cost in dollars of producing X items in a factory each day is given by this function C of X. Okay, so they've calculated labor, they've calculated raw materials. Okay, evidently it costs $5 just for the raw materials to produce each item. The labor they've been able to calculate with this cubic and quadratic portion. And then their fixed costs are $2,200. Okay? So that's every day. So we can find the marginal cost by doing C prime of X. Okay? So the derivative here is pretty easy. All right? C prime of X is going to be 3 times the 0.00013, so 0.00039 x squared plus 0.004x plus 5. Okay, that's C prime. That's the marginal cost function. Now this asks us to find the marginal cost when 150 items are produced. So if I plug in 150 into C prime, okay, we get 14.375. Okay, now what does this mean?
The cost of making 100, or the marginal cost of making 150 cars is $14.75.
Okay. So what do we mean by the marginal cost of producing 150 items is, we round it to the penny, $14.38.
That's how much more it's gonna cost to make 150 as opposed to one. Maybe? That's not possible.
This idea of marginal cost is kind of a tricky one to wrap our heads around here, but what that means is that if we produce 150, if we make 150 items, each one will cost us $14.38 to produce. Okay? So if I then took that number, and I'll use the unrounded number, 14.375 times 150, my total costs for the day there, or of those 150 items, would be $2,156.25. Okay, that's how much it would cost to produce all 150. All right, and by the way, since that's less than 2,200, that tells me that I'm probably not actually working for a whole day there. Okay, because it's 2,200 a day.
So in order to get the total cost, then would you just take the 1438 and multiply it by 150 plus 2,200?
Well, actually, to get the total cost, what we would do is C of X, or we would do C of 150. Okay? We would have to do C of 150, which we actually need for our next step. So C of 150 is $3,433.75. Okay? So each one costs this much to produce, or we could say the total cost is changing by $1,438. Or not $14.38. Okay? You could think of it as to produce one more, it would cost another $14.38.
So
Okay.
you get a total cost of 151, you wouldn't have to put it back in, you just add 14.
That's the idea, yeah. Now, part C here says find C of 151. So let's actually do that here. 151 cubed times 0.00013 plus 0.002 times 150 squared plus 5 times 151, 151 on all of those. Plus 5 times 151 plus 2,200. Okay, C of 151 is $3,448.18. Now if I subtract those two, 34, 33, 75, I get $14.44.
Yeah.
Okay? So you can see, treating it kind of linearly like this that gives us kind of an average. It's a little bit different than what C prime of 150 is. C prime of 150 gives us an instantaneous rate of change, okay? And that is one thing that we need to make sure that we remember, is that we talked about this a long time ago. The derivative gives us an instantaneous rate of change as opposed to an average rate of change. So the average rate of change between 150 and 151 is 1444. The instantaneous rate of change at 150 is $14.38. Okay? So we could even think of it, rather than each one costs that to produce, rather than thinking of it this way, we could think of it as the increase in costs is $14.38 to produce another item. Okay? That's another way you could think of this. Okay? It's kind of an odd, marginal cost. It's something that's used quite a bit, but it is kind of a tricky one to get our mind to understand here. So, to illustrate kind of the idea that we've got there between average and instantaneous, I'll just draw it real quickly here. Here's our 2 points. And actually, I'm going to kind of zoom in a whole lot here. So here's 150, here's 151. Okay? And you've got this curve going on here. Looks something like that. All right, we can see it's increasing. All right? What C prime of 150 gives us is the slope of this tangent line. Okay? And actually, you know what? I think I've got this drawn. Let me draw this just slightly different because it'll better represent it. It is increasing, but here it's actually, it looks like it's going to be concave up. All right? So we've got our 2 points, but at 150, we've got this slope of 14.38 or 14.375. Okay? That's the slope of the tangent line. So it's an instantaneous rate of change. When we did part C here, looking at the average, what that was giving us was the slope of the line through these 2 points. Okay? So, and that slope ended up being 14.44. Just slightly different, but again, it's kind of the difference between instantaneous and average. Thinking all the way back to the first day we did derivatives, the difference between the slope of a secant line and the slope of the tangent line. Okay? So that's the difference there. Alright, so let's look at another application here. This is kind of an interesting one. Find the rate of change in the area of triangle ABC as theta changes at the time when theta equals 60 degrees. Okay? So, we have our area of a triangle, and we're given that side AB and side AC are 12 centimeters and 10 centimeters. Okay, so how do we find area?
Half of base times height.
Okay, 1/2 base times height. We don't know the base or height here. Do you guys remember the other formula for area? When we know two sides and the angle between them? Not cosines is actually sine, but we do need to use trig. Okay, let's rederive it real quickly. Not too hard, okay? This is our height, right? So in this case, the base would equal 10. So the area is going to be 1/2 times the base times the height. Okay? Well, let's look at this right triangle here. Okay? We know, let's assume we know theta, and we know that 12. What equation could we write involving the h, the height? Sine theta equals h over 12. So, that means, not equals to, okay? That means that h has to be 12 times the sine of theta. Okay? So, let's say that we called this side C, since it's across from angle C. Alright, if we know two sides and the angle between them, then the area is going to equal 1/2 times the two sides times the sine of the angle between them. And one thing you might remember, we typically, instead of using B and C, kind of rolls off the tongue a little bit easier if we use 1/2 AB times the sine of angle C. Okay? The key here, though, is that you have side angle side. Alright, you have side angle side. You're using the two sides and the angle between them. Alright, so in this case, it's going to be 1/2 times 10 times 12 times the sine of theta. Okay? One half times 10 times 12 times the sine of theta. So, our area, in terms of theta, we're writing it as a function of theta, is actually going to be 60 sine theta. Okay? Alright, so that was the hard part. Let's go ahead and then and figure out what the rate of change of the area is. I'm looking for rate of change. What am I going to do?
You're going to take the derivative.
Take the derivative. Okay, so A of theta is 60 cosine theta. Yeah, A prime of theta. Thank you. Okay? Now, one quick rule here. In calculus, generally we use radians, okay? Most of our rules are derived for radians. So, what's 60 degrees in radians? Do you remember?
2 pi, 1/3, like pi over 3.
Pi over 3, okay? So, if I want A prime of 60 degrees, it's really A prime of pi over 3. So that's 60 times the cosine of pi over 3. You know, remember what cosine of pi over 3 is? 1/2, good. So that's 60 times 1/2, which is 30. And be careful with the units. If I'm in centimeters, this is gonna be square centimeters, it's a change in area as what changes?
As the degree changes.
As the angle changes,
Yeah.
okay? Now our unit of measure for the angle is the radian, okay? So it's square centimeters per radian. Okay?
That's interesting.
So the area is changing 30 square centimeters per radian. Okay? That's another application here. Okay? All right. We'll let you go. Have a great weekend. Okay?